Okay, we're going to go talk about Verilog, or Verilog HDL, which is the language we're going to be using in order to run all of our simulations inside of computer architecture. Real quick, I am presenting these, but I totally stole them from this guy.
It's not stealing because you cited your source. How do you say his name?
Right, it's not
plagiarism.
it's not plagiarism. That's correct. It might still be stealing because
It's just borrowing them.
Presented by.
What's it?
Presented by Bob.
Presented by.
Bye-bye.
You didn't know that my first actual title is by?
Oh, what does that stand for?
Bye-bye.
IDR?
It stands for that.
Biter. That's good. Thank you for pointing that out. Okay.
Or just keep it
So, all right, everyone think way back in the day before you were born and before even I was born. In the 60s, how do you think they designed these processors?
On paper.
On paper. So, and that probably made some sense. What?
Paper exists.
Yeah. Sure, I used the whiteboard.
That's not paper.
Oh, great. Something
It's
to,
also a wall.
Dave is laying down the law.
I hope he doesn't come up with something bad. I need to cancel that. All right, anyways. Paper, right. And that probably made sense when your transistor count was, I don't know, under 1,000.
Yeah.
Because even then you had a team of guys putting together. So the next step after that, we invented something called a computer, which we used these schematics to create. I know. So we came up with a program that probably did the diagrams, and by probably I mean we have programs that do the diagrams electronically as opposed to having to do them on paper and pass them, electronically, which was nice, but you still had to manually connect everything and simulate things by hand.
Oh, that's annoying.
It really is, isn't it?
So we program things to do it for us.
Thank you. And that got too annoying, so the problem is we still want to simulate this.
That's a computer. We really are like the laziest profession ever.
We are lazy, although math might be lazier.
Touche.
They may take the crown there, but we're
pretty close.
We're a close second if they win.
If we don't want to do it, we make a machine do it for us.
Exactly, because that's just too much work. All right. All right, so hold on. Before we go to this slide, let's forward here. Here we go.
Ooh.
The good old Intel 4004. Intel produced or introduced in 1971. Produced 2,300 transistors. All right, we need to cut that out. Where is this coming from? That's my question.
Walk the plank. What is going on?
There we go. Now hopefully that will never.
That?
I think so.
Okay.
Good. Whew. Well, that was
Appreciate
unprofessional.
the walk the plank message.
All right, introduced in 2,300 transistors. Do you think they could do this all on paper?
No.
Yeah. Well, probably.
Well, actually,
yeah, it's a large
I
company.
didn't think about that.
Yeah.
They
You
have
got
a big
hundreds of
room.
people. Yeah,
They
big
have a
room.
big room,
room.
and they have 2,300 workers who all did one, and they stuck it on the ground and stuck it together.
Yeah.
Yeah,
Right.
yeah.
So
Or
this
they
actually.
they have a huge piece of paper that
So-
they cover the ground with.
Right. So this definitely could be done with paper. It had a 108 kilohertz clock. The Intel Pentium 4 came out in 2000. Had 40 million transistors.
Oh my goodness.
Do you think we could do that with
No.
paper? No.
Sure.
No.
Stop it.
No. Could we do it with a schematic program? Yeah.
No.
No.
Take too long.
No. That would take well, okay. Could we? Yeah, and probably good
Theory.
20 years.
Yeah.
But yeah,
But nobody has
nobody's
20
got time for that. So we had to come up with something better. What?
Ain't nobody got time for that.
Nobody got time for that. All right. So what's the actual problem here? Well, when we're trying to design this guy over here,
Using the processes of the other one.
we really are, when we want to describe or simulate it, we're really talking about behavior. We're not looking at the exact how this transistor goes here. We're kind of looking at it from a top level. And let's see, manual translation of design to Boolean equation is very, very tedious and can be done with a computer. It can be very hard to handle these large complex designs, as I've just showed you. By the way, this was kind of cool because if you actually had a microscope, you could see it. This, not so much.
Colors. That's all you need.
Yeah. And we can still use SPICE for simulating digital circuits. Technically you can, but not pragmatically. SPICE is a program for electronic engineers that helps them simulate circuits. We can use that, but it would take too long. So those were the problems. And so Verilog is going to jump in and try and solve at least those problems. Ooh, good, the system design pyramid. Hopefully some of this makes sense. You know, the silicon's on the bottom, right? Then you have your circuit, aka where your transistors are, your gates, we talked about gates. Next is going to come your registers, how you build registers, how you put them on there and connect them. And then your chip will be a combination of all these gates and registers put together, and eventually become a system. What Verilog is going to do is you can specify on the circuit level, gate level, or basically chip register level, which will be your behavior, your data flow, or your structural mode. And then Verilog will kind of help you spit out something that can be etched to silicon. You still need to do layout afterwards. That's just something a computer really can't do very well, and we'll go into why.
Because they're not designers?
Yeah, they're not. Well, it's an NP complete problem. So it can't be done in practical time. Or at least it can't be done optimally in practical time. Okay.
We still have a job.
That's why we still have a job. So they need a simple, intuitive, and effective way of describing digital circuits for modeling. Yes, we always want something that's simple, intuitive, and effective. Are those three things ever something we don't want? I don't think so. So it started in the mid-'80s by good old Philip. And then 1990, Cadence opened the language to the public. And then it's been standardized in 95, and new standardizations have come out since then. Good old IEEE.
Good old.
I don't know why they show you this.
What the?
I don't like it. Skip.
Yeah, we should skip this. All right. This is what's important here. Your specification is what you write in Verilog. Hopefully you have your high-level design, low-level design, and you can eventually code it via RTLs. Guess we'll get to that in a minute. And then hopefully you'll have some type of simulation with Verilog that'll feed back and let you debug and test everything. And then once everything's working perfectly, you afterwards can use a synthesizer to place, and then you need to route it. It'll place and route, and then you actually need to do layout. That's not specified here, which then gets sent off to the machine for fabrication, and then they validate it afterwards, and you're done. So this all will work magically and beautifully, hopefully, with Verilog. Okay, what does Verilog look like? Okay, finally. So in C++, you have classes, or you may think of functions. In here, everything's a module, because every single piece has some inputs and some outputs. Right? We just have wires coming in, wires coming out. In reality, we just have wires connected to it. Just some of them are input wires, some of them are output wires. So a module is something that has input wires and output wires. Great. Right?
Wow.
Oh, hopefully. Unless you're doing test bench, and then it has no wires, which is just kind of interesting. But you have your port list, and let's go ahead and start coding this for class. So let me go ahead and...
That is the same background. You have
Forever.
If you want me to change my background, I'm definitely open to
The
options.
sea turtle picture that I have.
No, the little dragon chibi.
Verilog.
As soon as you were like, no, I was like, gosh dang it, chibi.
Yep, chibi.
All right, so let's see. Negated and.
Chibi with Apple Jacks.
Okay, so you start with module, and then you want to give it the module name, kind of like a class. You're giving it the class its name. So I'll call it. Now, normally I want to call it NAND, but unfortunately NAND is built in. So I'm going to call it negated and. And then you want to specify your input and output wires. So how many inputs are there to a negated and? Two. And we're really lazy with namings here. And how many output wires are there? One. 2 in, 1 out. Out 1. You end it with a semicolon, and then you do in module to specify when the module's done.
Is it necessary to put a space between the semicolon and
No.
the parentheses? Okay. I mean, I liked it. I just didn't know.
If you want to compile it, hopefully you've installed iVerilog. iVerilog star.v. Whoa. Is not declared within the module. And
iVerilog and Verilog are not the same.
iVerilog is Icarus Verilog. Verilog is the language. iVerilog is an implementation of it. Just like C++ is a language, but G++ is a tool you use to compile it.
Oh.
So if you install Icarus Verilog, which I think I told y'all to do,
Yes.
Yeah.
yes, good, you'll have iVerilog, which is just Icarus Verilog.
Alright.
Now, I tried to compile it, but it gave us some problems, probably because we haven't actually declared our ports.
Oh wow.
So,
Yeah.
by the way, this, fair warning, this compiler is not the best. Its huge disadvantage is that it's free, so it doesn't cost you thousands of dollars.
Yay.
Touche.
All right, so we need to declare some inputs. So you say that by using input. Wow. We'll call it wire in1 because these are currently wires. We are not dealing with registers. Input wire in1, input wire in2, and then we'll call the other one output, put wire out 1. Okay, so we've declared what's input and what's output, and we've declared them as wires and not registers. We haven't gotten to registers yet, but we're working only with wires, which is what we've been talking about. Hey, look, it compiles, and you can run it, but of course it doesn't do anything yet. Okay, let's jump back. Include directives, we don't care about that. Variable declarations, assignments, and other things. Okay, so what I've showed y'all here is the module name, port list, the declaration, and any parameters we want. Includes, just like import or include in other languages. And then your code, so to speak, goes in the body, which we're going to talk about next, and then you need your end module. Any questions so far about how I've set up in the code and that, hey, look, it
Can
compiles?
you just show us how you open
Yeah, open
the
it.
file in the terminal? Like the command that you typed in.
I used Vim. Use your
Okay.
favorite text editor. They're all just text documents.
Okay.
Okay.
I just wanted to make sure.
Yeah, it's all a text document.
So a Verilog file is a .v file?
Yeah.
It is, hold on. By convention, it's a .v. It doesn't have to be. It's Linux. It doesn't care. Extensions are superfluous.
Yeah, but we don't have Linux necessarily.
That's true, but it won't care in Windows either.
I don't
Or
have Windows
Mac.
either.
Or Mac. Oh, okay. It won't care in Mac either.
It will care on computers.
It won't care.
All right.
Anyway.
So just like in C and C++, you can type a comment with one line or multi-line comments. See, look.
Yay, comments.
Negated and. Great.
Yay.
Or I can write as much as I want
Oh, man.
on
No.
Oh no.
every line.
That's obnoxious.
It is obnoxious. And it's still compiled. Whoops.
Oh.
All right, we're putting this in a makefile.
I forgot about that.
Okay, good. So I compiled it and ran. Good. No problems.
Just make me make a file for everything.
I forgot about my
Yeah, makefiles are happiness.
They're happiness.
What was that, Jonah?
Nothing.
I don't believe you.
Everything's fine. Everything's fine.
Okay.
Sure.
All right. Here's another example. If you were to go and actually work professionally, it'd probably look something like this. Someone went to model the 8086, which is the one of the precursors to all the x86 processors. It might look something like this. We're not going to be doing it this in depth because we're not EE majors. We're computer scientists.
We're not what makes
EE, electronic engineers, EE. This is what they would be doing this.
Gross.
Electronic. Electronic web. All right, here's another example. Pretend you have, an ALU. Oh, I haven't talked about ALUs. So you want to do some addition or something. You might look something along these lines. Good morning.
Good morning.
If you don't put in the word wire, it's implied.
Okay, cool.
Now, we also have this other syntax, 3 to 0. Anyone take a guess what that means?
3 and 0 out.
Okay,
Or is it
No.
the opposite, right?
not quite.
No. Okay.
So,
3 inputs at low.
okay. So right now, all our inputs are how many wires?
2.
One.
One.
Everything is one wire. This is how you can specify more than one wire. So it's 3 to 0. So how many wires is that?
3.
4.
4.
Whoa.
Remember, 0 counts.
Oh.
Yeah, remember 0 is a very important
Those
number.
wires 0.
Yeah, you can specify wire 0, 1, 2, or 3.
That's silly. We're counting actual things now.
Now, hold on a second here. That's not silly. If you want to go to the first element of an array, what's the subscript? 0. That's right. Unless you're using a loser language like Fortran.
Unless you're using a loser language.
Okay,
What if I happen to like that language?
I'm okay with that. All right. So, there are many different coding styles inside of Verilog. We're going to try and stick with structural as long as it makes sense. For most of our process design, really the only time it doesn't make sense is when you have to deal with memory, and we'll get to that.
There's a lot of cross lines.
Oh, they just jump around. They jump over
Yeah.
each other, or actually what's happening, you have your board and it goes underneath and then back up. It goes, yeah, literally, well, it goes under actually. It doesn't go over, because it goes down with a via, over, and then back up.
Is she color coded?
They do. Haven't you seen a printed circuit board where it's green and then it has different little lines running?
Yeah, but I mean for this one.
Oh, well, yeah, they're like that.
They're lazy.
Okay, so structural is going to be the version that we have been looking at with the gates just recently, where you literally take the wires and then you specify a bunch of gates, and then hopefully it's fully connected on out, and then we call it a day. So let's go ahead and do that for our negated AND. So in order to code this, remember we want to do it after we declare our input and output wires, but before our end module. All right, when we use a negated AND, what do we use? What gates were used? And what was the other one? Inverter or not, right? So those are built into Verilog. So you can type in AND, open parentheses, and that's the wire you want the AND to go to. Now here's a problem, is that the AND doesn't want to go straight to out 1 because we need that to be
An output.
and we need that to be negated as well. So we need to have an internal wire. So we're going to take wire Y0. It's just very common to call them Y something for internal wires. So the AND, the destination of the AND is the first parameter, so Y0. And then which parameters are going to this AND? What are the?
1 and N2?
Yeah, N1 and N2. Now it might be weird why they did it this way, but the reason is you list the destination first, and then you list as many inputs as you want. So if you wanted your AND to have 4 inputs, you just specify them just like a function parameter. So this is going to hook up an AND between N1, N2, and hook it up to Y0. All right, we're almost there. The other thing we need to do is NOT. And what's the destination of NOT going to be?
Out 1.
Out 1, good, so we don't have to create another input wire. And then what's its source?
Y0.
Y0.
Magic.
Automatically.
Okay. Anyone confused?
Why is Y0 purple?
Because it's a standard variable name, so it colored it for me, the way it ran. Is it making sense? I just don't know how cybersecurity people are going to take this. Kinda? You okay? Okay, all right, good. We'll make sure it compiles. Good.
Yay.
Okay, so that's how structural is done. I will show you the other 2 ways. Don't use these ways until I tell you to, but we'll get to it. I just wanted to show you that there's other ways to specify it. You can do something called data flow, which,
Oh boy.
all right, that picture does not describe it whatsoever. Okay,
Gross.
and that picture makes it even less sense. Okay, never mind. I'm not showing you that. Here we go. Structural. This is what I just showed you with the AND and the NOT. So structural is where you're actually placing the gates down and saying where they go. Notice you didn't map or lay out where they are. You just say there's a NOT in between these wires. And then Verilog's going to take it from there. Data flow is going to look a little more C-like. You have a sign. That's probably the biggest key that you're using, data flow. Out equals, and then you're just going to specify everything as a Boolean expression.
What does this sound?
Select 0, select 1. This is a mux. So that's select 0 and select 1 are inputs, and then you have other inputs as well.
So a
I'm
different type
assuming,
of input.
I'm
Yes.
assuming the squiggle is a not.
Is a NOT. So the squiggle's a NOT. That's an AND. You can do parentheses to say which happens first, or and then et cetera, et cetera.
That's the same knot in.
These two are actually the same, just this one's written structurally, and this one is written via data flow, via Boolean expression. All right, everyone okay with this one down here? Don't do this at first, and the reason why I don't want you to do this at first is it's confusing
Yeah, let's not.
until you get,
No way.
what?
Let's not.
It doesn't look confusing, I know it doesn't.
Let's not.
Yeah, but it gets confusing. All right, behavioral is far more even.
Oh, I was about to say it looks like a case.
It's a select statement is what you're doing. This one's more confusing. You have to always add. Basically, what this is saying is if any of these wires change, execute this piece of code. So once these wires change, execute this. Begin, open, like AKA open parentheses, and there's the end case, AKA close. I mean, there's the end. Sorry, the begin, the end, close parentheses. Case, AKA switch or select.
Oh, yeah.
You're fine. I just wanted to give you that look. So you have two input wires, and this specifies if it's 0, 0, then out equals in 0. If it's 0, 1, out is in 1. If it's 1, 0, out is in 2. If it's 1, 1, out is in 3. Otherwise, it's X, which I haven't told you what that is yet. But I wanted to show you a different way of modeling it. All right.
So don't do them.
Don't do this one, at least not yet. Which one of these three do you think is the easiest to synthesize, aka take the code and produce a piece of processor from it? Structural, yeah. The structural is actually the easiest. It turns out with a good compiler, it can do just as well with data flow. It just takes a little extra work and then you're done. So data flow and structural end up being very easy to synthesize. This is not. This is a lot harder and sometimes cannot be done. So you always want to avoid behavioral unless you have to do it, aka you're dealing with memories, which of course we'll get to.
Unless it's for a lab.
Yep. Okay. So as I mentioned before, so far you've had two values, 0, aka low voltage, and 1, high voltage. Hopefully you'll have talked to philosophers, in which case you realize that no question has only 2 answers. So similarly, this one has 4 states that you can have. So it's either low voltage, high voltage, we don't know what it is, or it's not connected to anything.
Wow.
It's just there.
Yeah, it's just there. Okay? So 0, 1, we've talked about. X, the simulator can't figure out what's going on. Or high impedance, it's been disconnected. You get it? Good.
Yeah, I get why it's a Z.
I don't get the picture. It looks weird.
What is this picture of? Remember I took
Those are
this.
supposed to be the feet.
Yeah, these are.
I think it's like a
Why is he all strangled?
Oh. Someone didn't put their wires on right.
Okay. There's different ways to represent the data. The B.
Isn't that like where you can choose your voltage based on where you pick it off from?
Yeah, I've just realized that his feet has been melted together. So that's not good. We don't know what's going on there.
Not. Why is he
Oh, that's
smiling?
good shit.
That's not okay.
No, this is more like, please, someone help me. All right, you can represent these bits with B to just binary, so 6 bits. 1, 2, 1, 0, 0, 1, 0, 1 to represent the bits. You can also use hex. The first number is the number of bits again. The first number is always the number of bits. Single apostrophe hex, so 2, 5, which would be probably this, same thing up here. Yeah, because 8 plus, or not 8, so 4 plus 1 is 5, and then over here those 2 are just 2. So you can represent the same value with binary or hex. This is really good when you want to start doing a test bench. All right, skip that. Test bench, there we go. These slides are not right. There's a slide missing.
I mean, you took them from somewhere else.
Yeah.
You can't get too picky.
Yeah, I can.
I mean, you can, but
Isn't that the millennial way?
I mean, you are millennial.
Right, technically I am, by 1 year. If I was 1 year older, I would not be. But apparently I am.
Discovery.
What?
He's a millennial.
us
We're not
can't.
millennials. We're like generation like Y or something.
Why is millennials?
Oh, generation
Z, yeah.
That's it. Yeah.
Okay,
With letters?
so hopefully, yeah, we're letters.
Downgraded.
Hopefully, as we've talked about with Meltdown Inspector, you need to test your code very thoroughly. And Verilog actually is very nice about this. You create a separate module, which is your test bench, in order to actually test your code. So let's go ahead and see what that looks like.
You do something.
I know, right?
Da-da.
Gonna create a new tab. I'll call it negated and -test.v.
Oh, test files.
Module. Everyone okay? You sure?
Oh yeah,
All right.
I'm ready.
You ready for this?
I think so.
All right. Negated and test. We're not going to have any wires going in or out because,
Wow.
well, we don't care about that because
That's
we're just
true.
a test bench. And I always forget if there's a semicolon after that last module. No,
No.
good. All right. So first off, we want to have our input wires, which need to be registers. And the big difference there, I guess this slide was important, is that a net, aka a wire, is a connection between hardware elements. A register stores a value. We'll talk about how it actually stores it later, but a register is actually going to store a value so it can actually generate a high voltage or a low voltage, while a wire just connects things.
Yeah.
All right? So if you got to test something, you got to start it from somewhere, so therefore it needs to be a register.
Yeah.
So we're going to have register,
All right.
or actually it's just called reg because the rest of that's way too much typing.
Again, lazy.
A and B.
Woo!
Yeah. And then we'll have a wire called C for lack of great namings, which is the output, isn't it? Okay. Negated and, but you got, like a class, you are instantiating the module, so you must give the object or the module a name. When you're testing, it's very common to either use device under test or you can use unit under test. But I'm going to call it device under test, the DUT.
Under debt.
The inputs are going to be A and B, and the output will be C. Let's double check to make sure we got that right. N1, N2, out 1, great. And then 2 registers input, and the C is output. All right, perfect. Now this is where things get a little different. You notice over here in our test bench, we need to have initial begin. This is kind of a way to say, all right, now we're going to actually start coding something, as opposed to structurally connecting everything. We're actually going to write a little piece of code.
Yay.
Yeah. So initial, which means when the simulator starts, do this. Begin, open parentheses. We'll go ahead and put our in parentheses. 1, 2, 3, 4. So let's go and give A the value of 0, and then B, the value of 0 as well. Okay. There are different ways to assign values to registers. For now, always do it this way. If you do it a different way, sadness is going to occur. What this is saying is you apply these values in parallel, you don't wait or anything like that. So A and B are both going to be applied at the value 0 at the same time. Now, after it's applied, we need to give the simulator some time before it can for it to propagate the signals and actually give us the right output. You do that by putting pound and then the number of cycles you wish to go by in your simulation. So I'll just pick the number 5 just to give it something. And then afterwards you can at least do basic debugging by using something called display, which works very similarly to the printf statement. So I can do display C equals %D value C. Okay? So I'm applying 0, 0 as input to the device under test, which is a negated and, waiting 5 ticks, then I'm printing out what C is, and then I end my simulation.
All right.
Any questions on what the code is doing?
Why'd you use %D?
Yeah.
Just like in printf, remember it's %D for decimal.
Oh, okay.
I'm not decimal. I forgot what it stood for. I don't know why an integer is %D. I always forget.
So would C be 1 then?
Because it's a decimal.
Z? Oh, C.
C.
Right. So because the and of 0 and 0 is the and is 0, 0, 0, 0.
Negated and.
Then negated is 1. Correct.
So it should be 1.
It should be 1. Let's see if I coded this correctly. Hey, look at that.
Whoa.
Whoa. All right, let's go back. Let's do some good copy and pasting. Put a 1 right there.
The one there.
One. Actually, you know what we really need to do?
Whoa.
Let's go back up here and say A equals %D, B equals %D. And that way, we're printing out A, B, and C. All right. So these are the 4 different combinations. I need to turn off my phone. All right.
Texting in class.
I know,
Did
right?
you get a new phone?
Yeah, someone gave me a new phone. I mean, not gave me, I had to buy it, but
Okay.
I finally I finally upgraded to a Nexus 5.
Oh, okay. Oh, okay.
Not the Nexus 5X.
I got
What's that?
the
I was like,
Galaxy
somebody gave me a
8.
new phone, but there was a transaction of money and
That's sad. I noticed this.
there was an exchange of goods.
Oh yeah, the other one. Well, all of a sudden I didn't get a data connection, which actually wasn't that bad because I can just use Wi-Fi. But it started getting annoying, and then someone offered to sell me a phone for $50. And I was like, all right, fine.
Oh, okay.
Well, that's not too bad.
I'm not that poor yet. I know who I'm talking to, but yeah.
That's what I say.
If I was in grad student, it would not happen. No. All right. So are these outputs? They look good.
Yeah.
Sure.
Sure. Okay.
That's right.
All right. There's also actually a very nice program called GTK Wave, which means we can have a graphical view of what's going on. I know.
Oh, I want to see this.
This is going to be very, very, very helpful. Yeah, well, we're going to show you. You're going to want to use this when you get started because it's going to help you visualize what's going on.
A graph.
Graphic view. Anyway,
Pictures.
you have to specify where you want the dump file to be when you run your simulation,
I like the word
and then you tell it what.
I don't like the word dump.
I did. I thought it was
Dump
funny.
file.
And then you want to tell what
Jumping
variables you wish to dump as well.
Emphasis on dump.
And then you use GTK Wave on the file that contains all your dumps.
We're gonna have
Poor
we're gonna have a problem with like the X-Min G again.
What's that, sorry?
We're gonna have to run like X-Min G again and like display equals 0.0.
Yeah, if you're doing this from Bash, yes.
Poor babies. Just dumped instead of
Variables are not babies. Stop it.
Stop thinking that variables are people.
Variables are not
people. All right. Negated and .vcd is where we'll
We
dump.
should have named it the negated dump file.
And then
Negated dump.
I kind of always forget the syntax, like dump vars, and
Yes.
then what was it?
0 dump.
Oh, 0, which is where you want the dump to begin at time cycle 0.
Oh,
And
wow.
then the unit you want to dump, which is the DUT, the device under test.
So if you had it as a UUT, it would be UUT in that spot?
Yes.
Okay.
And up here is just the file name. All right.
So proud of you.
Thanks.
It's here.
All right, and then when you compile and run it, remember I'm recompiling it each time. Dump file negated.vcd open for output. All right, so now if we do GTK Wave on the dump file, he was on a surfboard, on a surfboard on a circuit board.
Yeah, that is.
Wow.
So we select our device under test, and then we can select which wires we want to look at. Maybe we want to look at in1, in2, and in and out. We can append those. So when in1 is low and in2 is low, out1 is high. And then notice that it changes. That still stays high. These guys finally change. It still stays high. But then when he finally goes back to both being high, then the output becomes low. So you can actually select which wires. Like we could also add that internal Y0 if we wanted to, which doesn't, kind of a little confusing at first. Well, it's just the exact
It's
mirror.
the opposite of output 1.
Right. If we
Yeah.
wanted to watch that one as well. So hopefully you can see this is very helpful in trying to determine what is going on with your program. Yes? Come on. If you're going to be at the peanut gallery, you got to speak up. Loud and proud.
Just getting gum.
Just getting gum? All right. What?
You know, remember this SpongeBob episode where Patrick makes him stand on top of his house and he just goes, "I'm ugly and I'm proud."
Okay. Obviously, you can always print with display, just like printing with regular programs. When things start to get complex, it's going to be hard to actually follow it. The GTK wave thing is actually pretty nice, so please use it. Okay, delays.
Oh, that stupid thing again.
Man, you
I
were
don't think
just,
that's
you're
an-
bitter.
I think that's an R. It's like default.
So, hopefully you've seen with gates, there's a delay.
Why does it
Because
have
it
a
has to go through all the different circuits. If you recall, the electric flow has to saturate before the gate finally produces its output from its input. In other words, do the gates happen instantaneously?
No.
No. So they all have a delay. You have to specify what you wish that delay to be inside of Verilog when you're doing the simulation. And you do that by adding that whole pound and then a number, how many ticks you want it to delay.
The cycles.
Ticks, you can say cycles, but let's say ticks for now, because a cycle is going to be something different that we'll talk about later. So how many ticks you want it to go by. So let's go back to our negated AND. Let's say that the AND, for sake of argument, takes 1 tick, and our NOT takes one tick as well. So how many would this take in total?
2.
2, in general. So I'll go ahead and save that. I'll recompile and run it. We're still good, because if you actually looked at our test file, we wait 5 ticks between each one before we output, so that's still within the timing constraint. Yeah, phew. Okay. Now if we look at from GTK wave, we're actually going to see the timing difference. Actually, let's look at these 3. So,
Red.
yeah, why is that?
Because it's not like.
It took it 2
Get it
ticks
out
before it
there.
could figure out what it is. So red means X. I don't know what it was.
I don't know what he was doing.
If I were to actually add Y0, it actually took it a full cycle before it became available. Really the interesting part is over here. When we go both high, you want out 1 to go low. So when both went high, that's when Y1 after 1 tick went high, and then the NOT took another cycle to saturate and then go low. So with GTK wave, you can actually start seeing the delays with everything, and that will also help you significantly. All right. Any questions?
No.
You actually have everything you need to do your lab assignment now. Yes. Yeah.
So that's what we're working on now, right?
And a bit. Okay. So do we have anything else?
All
All right. Things to keep in mind. This is a different programming model. Verilog is concurrent. It is not necessarily the case that one of these happens before the other. They're actually both happening at the same time. What's going on is since the AND takes a cycle before it can, or a tick before it can complete, the NOT is going to implicitly take another in that case. But just because they're written this way doesn't mean anything. I could do it. I could reverse those two, run it. It would do the exact same thing. So it is concurrent. You have to keep in mind that things are happening concurrently throughout the entire simulation. It's not like programming where it's one after another. Is anyone confused by that?
If you put like a 2 for like the NOT part,
Mhm.
would it take 1 second longer, or would the
One
AND
tick
then
longer.
would-
No, because in this case, the NOT is coming after the AND. You can see by the fact that the output of AND is an input up here. If these were not connected and they were completely separate, then it would only take 2 ticks in total.
Okay. So
Good question.
So basically, since the NOT relies on the AND, you just add the number of ticks from the AND to the NOT.
Correct.
Ticks.
But if we had a very complex circuit where we had different things going in parallel, it's only you have to go and evaluate the longest path, which we'll get to
Okay.
later on. Yep.
Oh my gosh.
Yeah, let's not go back to that.
I don't want to go back to that class.
Which one is this?
System analysis and software design.
I was like, you haven't taken
It was like-
algorithms yet.
No. It was. She was talking about the critical path.
Oh yes, the critical path. Yeah.
Yeah. I
Okay.
hated that class. I don't know how I got A.
All right.
No.
Any other
Oh my
questions
God.
about Verilog that we've done so far? I've tried to keep it simple and straightforward. Try not to make it too complicated. Oh yeah, the review. Sorry. Concurrent. Think while you're writing your program. Okay, that obviously is.
No, I like to bring this.
There is blocking and non-blocking code. Let me spell this out. This really goes back to concurrency. Non-blocking is concurrent, namely, This is not blocking, aka the not doesn't have to complete before the and starts. These are both happening at the same time because they are non-blocking. Your test is blocking because all of these statements have to wait. You have to wait 5 ticks here before you can go to the next. So there is a block here. So keep that.
Blocking is the waiting.
Yeah, the waiting. Also, please, again, always do your assignments this way. If you ever do that, it becomes a blocking assignment, which means it waits 1 tick before it continues, and your code is going to become really, really confusing. Don't do it that way. Okay? Leave it like this for now. It'll become, your life will be happier. Trust me.
Your life will be happier. Not you, but your life.
Your life. All right, I think that's it. Here's some links if you really want to look into more of it, but I think I covered a good majority of it.
Evita.
Are there any questions?
Yeah.
Whoa, how'd that happen?
Well,
Here we go.
see.
Any questions on this one? Okay, great. I will stop the recording.